To briefly review what we've been through, because we've been through a lot of complicated technical reasoning, and you might not be able, some of you at least might not be able to see the forest for the trees, or indeed to even see the trees for the leaves. And, I'd just like to devote 2 or 3 minutes to sketching out what happened during the last 2 weeks. Firstly, we refounded scattering theory on a basis that was, we gave a description of scattering theory on the basis that had nothing to do with any approximation scheme and had nothing to do with any artifactual features like adiabatics turning on and off. We proved the reduction formula, proved in my usual hand-waving sense. The formula that tells us if you know the Green's functions exactly, then you know the S-matrix elements exactly, and a fortiori, if you have an approximation for the Green's functions, you have an approximation for the S-matrix elements. Secondly, we gave a new interpretation to, at the moment, our only approximation technique, Feynman perturbation theory. We showed that Feynman perturbation theory was, in fact, a perturbation theory for the Green's functions when the lines were off the mass shell and we took account of all the trivial kinematic factors in the way I described. However, Feynman perturbation theory is, in fact, many possible perturbation theories, because there are many possible ways of breaking a given Hamiltonian up into a free part and an interacting part, in which each such breakup you get a different expansion. The most naive way of breaking up the Hamiltonian, that is simply taking the cubic and higher terms and calling them the interaction, and all the quadratic terms and calling them the free Hamiltonian, leads to an expansion which, although perfectly valid, or at least as valid a priori as any other expansion, is not particularly useful. It is an expansion for the wrong Green's functions, those of the unrenormalized fields, in terms of the wrong coupling constant, the difficult to observe bare coupling constant, with the wrong parameters held fixed, the bare masses. We corrected this difficulty by rewriting the breaking the Hamiltonian up in a different way, where the free Hamiltonian was given in terms of the renormalized fields and the physical masses, and the difference between that and everything else was the interaction. Such an expansion necessarily generated counterterms. Of course, there is no way of telling what the counterterms are until somehow you insert into your computational scheme the definition of the parameters you call mu and the quantity you call phi prime, etc. And therefore we went through a long song and dance in which we found how to define those things consistently within our perturbative scheme, that is to say, as Green's functions, as properties of Green's functions that gave us the definitions of the physical masses and the physical coupling constants and the renormalized fields, and inserted into our scheme explicitly the definition of mu, m, phi prime, g, etc. Now, in the course of this, we went on many excursions. So this is the general outline of what we've gone through. On the course of it, we went through many excursions and found many interesting things that will be useful outside of the development of this computational scheme. 3 of them in particular will be very important to us later. One is we found the spectral representation for the propagator, which comes up in other contexts of physics. Secondly, we learned the law of loops. That is to say, we learned how to reduce any Feynman integral from a momentum integral into an integral over Feynman parameters. And thirdly, we encountered and conquered, at least in low orders, the infinities that occur in Feynman perturbation theory, which from this way of view looking at things are a total unexpected surprise. But we found that, at least in the low orders, for certain simple theories, they could be absorbed by the renormalization counterterms. On the other hand, it was easy to construct theories for which the infinities could not be absorbed by the renormalization counterterms, and I discussed them at the end of last lecture. Of course, we did not prove that our theories, as with cubic and quartic interactions, are renormalizable in the sense that all infinities that occur in all orders are eaten by the counterterms. We just showed that they were not non-renorm. No, we didn't show that either. We just showed that in low orders it happens, and we postpone until a future date the question of whether it happens to all orders. Okay, that's the summary of what we've went through. I gave that little speech because people have been saying they didn't know what was going on. Now you know what was going on, even though you may not know the details. Now I call for questions. Yes, sir?
Last week or the one before, you were working with states, both states like F1, F2,
Mm-hmm.
states like F1, F2 in.
No, I never talked about F1, F2. Well, oh, I'm sorry. Yes, I did.
Bring it in with you, will you? Tell them we're returning first thing in the morning.
Yeah. Well, F1, F2, in or out, okay, are the states that look like two particle states in the far past or the far future, depending upon whether it is in or out, where one of the particles is in a momentum wave packet characterized by the function F1, and the other one is in a momentum wave packet characterized by the function F2. Is that clear? Okay, F1, F2 is the corresponding state in a theory of free particles that have the same mass and spin as the physical particles. Okay. F1, F2 is the state that is the descriptor, if you wish, of either the state F1, F2 in or the state F1, F2 out. Okay?
And the mathematical definition is integral over capital F, K1.
Yeah, in a free particles theory. That's right. I forget my where I put all the 2 pi's. I think I had something like to a host of kinematic factors which you cannot expect me to remember. K1, K2 in a free theory.
Right. Okay. And you also commented that the limit as t goes to infinity of your phi F1 at t operating on an F2 gives you F1, F2.
In or out. For one particle state, I don't have to specify in or out. A one particle state looks like a one particle state forever.
Yeah, the thing that confuses me is F1, F2 in or out is time dependent.
No, these are Heisenberg picture states.
Oh.
All of the time evolution is being. I mean, I could have done the whole thing in Schrödinger picture. It's just when if you wish, the equations that are on the board. This is phi prime F1 of t F2 depending with a fixed state. I happen to do all my computations in Heisenberg pictures, so if you want to understand what those equations mean, they are Heisenberg pictures equations.
You say the F1, F2 in state becomes a two-particle state at t equals minus.
It looks like. I don't say it converges in the sense of strong convergence or anything.
But then in the Heisenberg picture, of course, it doesn't change at all the time. So you just mean the Schrödinger.
Well, but in the Heisenberg picture, yeah, there's a one-to-one correspondence between Heisenberg and Schrödinger states. And in the Heisenberg picture, how I would say it is that if I look at the expectation value of any observables constructed from field operators in the far past in such a state, that's the same as the expectation value of those observables in a free particle state.
Can I ask one more thing? Is phi prime at F1 at t, F2, what is that at finite time? That's not F1, F2?
It's nothing. It's a hideous mess. It's a combination of 2 particle states, 3 particle states, 4 particle states, 217 particle states.
And F1, F2?
The time limit is a filtering process that pulls out the...
Right. And can you write F1, F2 at finite times in any analytic point?
Mm-hmm. Well, this is a Heisenberg state. Sure, it's EVI, or if you want...
Without the F1, F2?
No, that's meaningless. That's because production takes place. The statement, where in the Hilbert space is a 2-particle state, is a meaningless statement. Proton, antiproton goes into 13 pi mesons. Okay? You don't have to know anything about the underlying dynamics if you accept that that process occurs. there is a state that in the far past looks like a two-particle state, proton and antiproton, and the far future looks like a 13-particle state, among other things, 13 pi mesons. Okay? To ask, is it a two-particle state or a 13-particle state without saying past or future is a meaningless question.
What if you ask the question in two-particle state at time 0?
I don't know what the answer to that is.
It's a hard question to...
No. I expect there are 20 billion different definitions depending on how you wish to define two-particleness at time 0. I know clearly how to define it at plus infinity and minus infinity, where all the components have gotten far from each other and they're all a billion light years from each other, and I just go through the universe counting the number of particles. When the whole thing is on top of itself, I don't know what the definition of number of particles is. I'm sure there is one. I'm sure there are 20 million. An infinite number in all probability, and you tell me what definition you want to use, and I'll tell you the average number of particles in that state at time 0. Okay. But until you tell me what the question is, I can't tell you what the answer is. Okay.
Well, when you define, everybody's laughing already.
It only eggs them on if you call attention to it. Go on.
Well, when you define gamma prime, you define it with the convention that all the momentum are pointing inward.
That's
now,
right.
If some other person that didn't know that convention used a different convention, would you get the same result anyway?
Yes, since I define gamma prime as a function of p squared, p prime squared, and q squared, and therefore it doesn't matter whether I talk about q or minus q, p or minus p. Okay. If I had written it as a function of p squared, p prime squared, and p dot prime, then it would depend on which convention you used.
Okay.
Okay, is that a satisfactory answer?
That's fine.
Okay. Yes, sir.
Yeah, when you talked about the experiment using Mason on scattering,
Mm-hmm.
well, one part of the amplitude looked like G, 1 on S minus M squared G.
And the other part was free of poles.
Right. Now,
By guesswork. I mean, I didn't prove that.
well, what you really mean by G there is G as a function of S. which approaches.
But the residue of the pole,
Right, but you really mean, yeah, it's not really G until S is equals M squared, right?
I know, but the remaining part doesn't make a pole. It's gamma of p squared is on the, let's look at the graph. I don't put blobs on things. Okay, oh, they're all blobbed. Okay, it looks something like that. So it's gamma prime of m squared s mu squared, okay, quantity squared, one on one side and one on the other, okay, 1 over s minus m squared, okay?
No, I understand.
That is gamma prime m squared, mu squared, quantity squared over s minus m squared plus no pole term. Okay, I'm assuming, of course, that this thing is analytic in the neighborhood of s equals m squared, so I can expand it in the power series. The terms of order s minus m squared and higher just give me analytic terms, which I shove into the other terms. Okay? Fred?
When you were doing pi prime calculation for order G squared, you had 3 terms in it. So pi, f, a b term, and a c term.
That's right.
And the total combination is convergent. Pi f isn't convergent. And just calculating out b2 and c2.
C2 is convergent and B2 is divergent.
Yes. Is there any significance to the fact that one of them is convergent and the other is divergent?
It just has to do with the extremely mild divergent structure of the theory. If we were doing 5/4 theory, we would find both B2 and C2 were divergent. The integral is for 5/4 theory has 8 powers of momentum in the numerator from the integration and 6 powers in the denominator from the propagators. It is quadratically divergent. That means its first derivative with respect to p squared is still logarithmically divergent, and it's only a second derivative with respect to p squared that is convergent. Because whenever you differentiate with respect to p squared, you drag an extra momentum integration into the denominator. Thus, in this theory, I would have both divergent mass and wave function renormalization counterterms.
How well do you know the analyticity of two-point function at small momenta? Are you really
The two-point function I know perfectly at small momenta.
Is this the math?
The propagator, or you mean this thing here? Which are the gamma prime, the three-point vertex? It's known that in all orders of perturbation theory, it is analytic in that neighborhood.
Even if the normalized math?
Oh, that's the problem of infrared divergences. We can get, which I talked about briefly. Feynman integrals can also blow up at k squared equals 0 if they are if there are no masses in the problem, as well as k squared equals infinity. And there is a whole song, a separate song and dance one has to go through if one wishes to treat those divergences separately. I will probably, well, no, I'll just say possibly. I don't want to postpone all of the last 20 years of physics to the second semester of this course. I will possibly go through that song and dance at some length. But it's a separate problem.
I didn't want to push you with the song and dance, but you might want to say a word about the arbitrariness of the renormalization point here.
Yeah, I mean, I picked a definition of the mass. The wave function renormalization is something you've got to choose just right. Otherwise, you don't get the right S matrix elements. The mass renormalization is something that, in principle, you might say there's an amount of arbitrariness in it, but any sensible person would define the mass in the same way as any other sensible person, the energy of the lowest state with the same quantum numbers. The coupling constant is much more a degree of freedom. We have much more freedom of choice. I picked one that I said was super convenient, and here it is, and I showed you why it was super convenient. But super convenient is not the same as being inevitable. If there are problems, for example, I could have defined this at some other point. Then I wouldn't have it as the residue of the pole, but I would have avoided any problems of divergences that arise as special values of the momentum if they occur. Okay, so that's a possible difficulty in this detailed prescription, but how to get around it is trivial. Okay, you lose the wonderful advantages of this coupling constant, but you still have a definition of the coupling constant, which is all you need. Other questions? Yes, sir.
The graph you drawn up there, I don't see why you don't have two propagators, S minus m squared, and two sections joining the one pi.
No, it's IPI, full propagator, IPI. If I consider a graph, here's a typical one of the sort you're considering. Okay. Have I put arrows everywhere? No. Okay. Okay. These two things just combine together to give a correction to the single propagator. And likewise, if I had 72 of them in the row, they would just combine together to give me a single propagator. Okay. This part in here is not IPI. It's the full propagator, not the self-energy matrix. Okay. This thing here equals, I don't know why I keep saying I, 1 pi. 1 pi dot 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 dot. Okay. And then 1 at the end. It's this whole sum. I sum up all the 1 pi insertions in the middle and get a single propagator. Okay?
How about the parts joining the middle to the two outsides? Let me have two propagators there.
No, I have one. This whole sum here, you're thinking of it in this way. This with 1 pi insertion, this with 2 1 pi insertions, this with 3.
So you summed that up and got the part in the middle.
That's right.
And you got the two 1 pi on the other side of it.
No, yes, that's right. They carry no propagators.
And then there's the lines joining the middle of the two.
No, they're part of this blob. I mean, that's the way to think about it if you want it to come out right. Okay, those explicit lines are part of this blob. Yes, sir.
Why does the phi, I didn't calculate, why does the phi to the sixth counter term take away the divergences in the phi to the sixth theater?
Well, because we have a graph like this. Okay? To cancel that graph, we need a counter term with also 6 external lines. Otherwise, it doesn't contribute to the same Green's function. That's a phi to the 6th counter term. Okay, phi.
But that just means we need the counter term. That does not make it clear that it cancels the divergences.
Well, in this case, it's trivial because this is simply our good old integral. That's only logarithmically divergent. So one subtracts the same integral we encountered in our pi prime computation. And you subtract the value of that integral at any particular point, and you get a finite result. Further questions? Okay. Now, I would now like to just a discussion of Lorentz group. I obviously have these in the wrong order. Here we go. Oh, I just put them down. 1, 2, 3, 4. Okay. I would now like to turn to the remaining loose end in our general theory. The one computation we have not redeemed in the new formulation of scattering theory. The computation you did in problem 5, where you computed the lifetime of the phi when the mass of the phi was greater than 2 nuclear masses. What?
Is that
Was it phi? Whatever it was. It was 6, 7, problem 7. Did I say problem 5 when I wrote it up? Yes, I meant problem 7. I apologize for that. People are going crazy trying to find that computation in problem 5. I hope you caught on. I hope you caught on to what I meant after a moment's thought. I'm so, if you don't, don't admit it. Now, in order to study this, what happens if we try, of course, in our formulation of scattering theory, the concept of an unstable particle never emerges. If there's an unstable particle, there's an unstable particle. You just forget about the field associated with that particle, since that particle never appears in asymptotic states on account of it decays, so long before the time gets to be plus or minus infinity. And you just compute scattering matrix elements between stable particle states. Nevertheless, it is amusing to ask the question, what would happen if someone who had no physical intuition whatsoever decided to follow through our computational scheme and decided to choose mu, the mass of the renormalized mass of the meson, to be greater than 2m. He would surely must run into trouble. He can't make it a stable meson with mass greater than or equal to 2m. But what is the trouble he'll run into? Well, before I answer that question, I'd like to derive an identity that has nothing to do with whether or not there is a stable meson or not. And that is an identity for the imaginary part of pi prime that appears at the beginning of the first of the 2 problems I gave you this time, and will be useful to us in our investigation. K squared minus mu squared minus pi prime is related to the inverse propagator. Thusly, or I guess a better way of writing it would be minus I d prime inverse. Now, we can therefore deduce a formula for the imaginary part of pi prime using the fact that for any function, the imaginary part of f is minus of f inverse is minus the imaginary part of f over the absolute value.
Where are you?
A trivial result, a consequence of the definition of the imaginary part. And we have a formula for the imaginary part of minus I d prime. So we find the part of prime. We're always talking about real k squared, because that's where we have the formula for the imaginary part, is, well, we've got an absolute value, so I have d prime to the minus 2 quantity squared. And then I have the imaginary part of d prime, which is pi. That's 3.14 sigma, as I recall. And I'll check that. Yes, sigma of k squared. That was the formula we got from the propagator. Now we have an expression for sigma of k squared, so we can write this as, in fact, I'll choose to write it as, is there a minus sign in here? Yes, it's minus pi sigma. I can write this as minus 1/2 d prime of k squared to the minus 2 sorry, not an integral. I wasn't using integral notation. Sum over intermediate states n phi prime of 0 vacuum quantity squared 2 pi to the 4th delta 4 of k minus pn, where of course not only is k squared real, but k naught is greater than 0. Otherwise the answer would be 0. That was our formula, which we derived in our discussion of the propagator for the imaginary part of the propagator. It shouldn't be squared, yeah. So, sip of the chalk. Now, we'll use this formula very shortly. A significant feature of this formula, which we also saw last time, was that pi prime has an imaginary part at k squared for k squared greater than 4m squared in lowest non-trivial order of perturbation theory. Thus, if our imaginary dumb cluck who is attempting to go carry through the renormalization program for mu squared greater than 4m squared attempts to impose the condition pi prime of mu squared equals 0 for mu squared greater than 4m squared, he will lead to a complex counter term B2, because he has to subtract not just a real number, but also an imaginary number. He would have to really be a dumb cluck to not realize something is going wrong in this case, because he would realize that he is adding to his Hamiltonian a non-Hermitian operator by choosing B2 to be complex, and he should know, even if he doesn't know anything else, that that's bad news. Though this is not possible, unless you want to play with theories with non-Hermitian Hamiltonians, in which case you will have to do so as an extracurricular activity. Now, of course, this means that in this case our standard renormalization conditions are not applicable. Everything I say for the pi prime itself also go through for its derivatives. And in fact, from the pure viewpoint of scattering theory, we don't need any renormalization conditions if we don't want them for this particle, because this particle is unstable and therefore will never appear in the inside and outside of a scattering process, on the outside of a scattering process. So how we renormalize it is totally irrelevant. However, renormalization does also serve the purpose of eliminating infinities, and it would be nice to have some sort of conventions that eliminate the infinities. And the conventions I'll choose to adopt in the remainder of this lecture is simply to state that the real part of pi prime of mu squared equals 0, and the real part of d pi prime dk squared at k squared equals mu squared equals 0. These are just arbitrary and enable us to fix our subtraction constant in some way that's continuous as mu squared goes from below 4m squared to above 4m squared. They're certainly not forced on us by any general principle. I just adopt them because they will make this particular the things we are going to discuss somewhat simpler. So it's an arbitrary renormalization convention. It has no physics in it, but it's certainly allowed. I can fix those counter terms any way I want. Now I will attempt, using these conventions, to compute what the propagator looks like to order g squared. We did it for the case when things are stable. Let's now do it for the case where things are unstable. I will do it near k squared equals mu squared. Since I don't want to write horrible equations on the board. And in particular, I will treat a very small neighborhood of k squared equals mu squared. I will treat k squared minus mu squared itself as a quantity of order g squared. So I'm interested in the tiny region of the point on the real axis, mu squared. That tiny region is of size g squared. Now, the obvious tool for that is power series expansion. Minus I d prime minus 1 equals k squared minus mu squared. That's safe. That's of order g squared. We keep that. Plus pi prime of mu squared. Plus k squared minus mu squared d pi prime dk squared evaluated at mu squared, plus dot dot dot, which is of order g fourth, because it's k squared minus mu squared quantity squared. This term, in fact, is also of order g fourth, because we know pi prime is 0 until we go to order g squared, so we have g squared times g squared, which is order g fourth in the region we're after. And this thing we know from our renormalization condition has vanishing real part. So this is k squared minus mu squared plus I, imaginary part, of pi prime of mu squared plus order g fourth. That gets in all the terms that are of order g squared. Now we happen to have a formula on the left-hand board for the imaginary part of pi prime of mu squared. To order g squared, the diagrams that contribute to this formula look like this. The only thing that can have that, as I said earlier, the only thing a meson field can make to order g squared is a nucleon-antinucleon pair. Since the meson field is off the mass shell, the value of this diagram is minus Ig from the coupling constant, I over k squared minus mu squared, the lowest order propagator. That makes the contribution to order g squared. The k squared minus mu squared, if we look at our formula here, the k squared minus mu squared is canceled by the d inverse, which must also be taken to lowest order in g squared, squared. So what we have is really exactly the same matrix element we computed when we were doing the condition for the computation for the decay in problem 7. This differs from the matrix element we looked at in our old dumb theory of unstable particle decay, only by the factor of k squared minus mu squared, but we nicely enough have a d inverse in front to cancel that factor out. The only difference between this and the decay amplitude, here's my nice 2 pi to the 4th delta function, sum over intermediate states that comes into computing a decay amplitude, is that there's a minus 1/2 in front. So I have imaginary part pi prime of mu squared equals minus 1/2 times my old second order decay amplitude as computed in in the problem 7 times a, but of course when I computed the decay amplitude I had a 1 over 2m from the intermediate states, which I don't have here. 1 over 2m from the initial state, I'm sorry, in the decay formula, so I'll multiply by that. And this is gamma as computed in problem 7, a quantity of order g squared. Not m, mu. Mu is the mass of the decaying particle. Plus, of course, higher orders in g.
Which mass is
That is the mass that you put in the decay problem when you computed the decay. Mu.
that? So it's renormalized.
Well, renormalized, reformalized. Zeroth order mass. Zeroth order in g squared. Now, sticking this together, I find I have made a sign error. Let me check the equation. Yes, I have made a sign error because I made a sign error all the way up here. Minus. Forgot that. Sticking all this together, I find my expansion for the propagator. In this theory, I don't have to do any new computations because it all involves old computations. K squared minus mu squared plus I gamma as calculated to 0 order, mu, plus order g fourth. Or, of course, completely equivalently, k squared minus mu minus I gamma over 2 squared plus order g fourth, since gamma is a quantity of order g squared. Thus we see that the effect of the interaction that enables this particle to decay is to displace the pole in the propagator from k squared equals mu squared to k squared equals mu plus, I better put the complex plane here, k squared equals mu minus I gamma over 2 squared. Now, when you look at this drawing, you think I've gone, if this is mu, up here. When you look at this drawing, you may think I have gone bananas because there I've got a pole in the complex plane, and I proved to you that the propagator was analytic in the complex plane. The point is, however, that we're starting out above the cut and doing a power series expansion there. So we get a power series expansion that's valid in some circle when we go above the cut, and when we go down, we go through the cut into the second sheet of this complex function of a complex variable. I indicate that by a dotted line. That means you think of this as a circular disk of paper that is sitting on top of the cut and then go through the cut and extends underneath onto the second sheet. So this pole is there all right, but it's there not in the function on the cut plane, but in what we would get if we analytically continued the function from above the cut, that is to say the analytic continuation of the function to the second sheet. Those of you who took my 251 course or comparable courses should not be surprised, of course, to find an unstable particle pole associated with a pole of something related to a scattering amplitude on the second sheet. Are there any questions about this argument? Now, I would now like to investigate the physical consequences of what we have discovered in lowest order perturbation theory. and I would like to discuss in particular two features that are traditionally associated with unstable particles, the Breit-Wigner formula and the exponential decay law, and see how they arise in this formalism. I will totally forget the perturbation theory origin of these formulas and simply say my only assumption will be that I have some field and it has some propagator, and that propagator is of the form d prime equals I over k squared minus mu squared plus mu I gamma. I wrote them in a rather stupid order, but thank God multiplication is commutative. For some parameters mu and gamma, and for some range of the real axis, I of course don't need the I epsilon now that I've put in the mu I gamma. For some range of the real axis, for some range certainly isn't true everywhere. It doesn't have the right analytic properties, but I assume there's some tiny stretch of the real axis where this is an excellent approximation to the propagator. That certainly happens in second-order perturbation theory, as we've seen, but it may well happen in other circumstances where there's no trace of a fundamental phi particle, and you arrive at an unstable state because of some mechanism analogous to those which arise in non-relativistic quantum mechanics, where you have a bound state that's not quite bound. For example, only if you turned up the coupling constant would it become a bound state, and it appears as an unstable state or a resonance. So this is the only assumption I will use here. It is, and also I'm out of matches. Does someone in this vast horde of people have matches? Ah, thank you, sir. Oh, even earlier. Okay. Now, firstly, I will investigate the momentum analysis of an idealized production process where I imagine taking my Lagrangian that describes this theory, I could just call it rho of x, phi of x, turning on an external perturbation of the sort we've discussed so frequently before, of adding a term times phi prime to the Hamiltonian, or the Lagrangian, and I'll look at an extremely idealized case where rho of x is simply a delta function. Now, in that case, it's trivial to determine the amplitude for going into any given final state. That is to say, I just, at space time 0, at space point 0, at time point 0, I just bash the vacuum of the system with this field. I turn it on and turn it off, impulsive switching on. Perhaps I should insert a coupling constant here, G, or I'll call it lambda so you won't confuse it with any coupling constant that's in there, and see what comes out of the vacuum. Of course, that's trivial to lowest order in lambda. The amplitude for going to any given state is simply n phi prime of 0 vacuum plus higher times lambda plus order lambda squared, aside from phase factors, in which I'm not worried about, amplitude vacuum into n. And therefore, or I'll write proportionality too, since I'm not particularly interested in 2 pi's or anything like that. And therefore, if I consider the probability of producing a final state with momentum k, the probability of producing a final state with momentum k, which I'll call P of k, will be K could, of course, be any four momentum. That's allowed in the final states of the theory. Sum on n is proportional to sum on n, n, 5' of 0 vacuum, quantity squared, and we just want to take out the part lambda squared. We just want to take out the part that has momentum k, so we compute this quantity plus perhaps corrections of order lambda cubed. But I can keep lambda as small as I want, so I can suppress those corrections as much as I want to. Okay, I've just summed over all final states with a given momentum k. Don't worry, there may be kinematic factors in here, but I'm not interested in that. That's all washed into the proportionality sign. Now, near k squared equals mu squared, of course, this has a very simple formula because of this is precisely what appeared on the right-hand side of our expression for the imaginary part of the propagator. This is the expression that enters into the imaginary part of the propagator. So this is proportional to lambda squared, in fact, for all k, imaginary part of d prime of k. Now we have a ansatz for d prime of k and what its imaginary part is, and we just plug that in. This is proportional to lambda squared. Let's see, the imaginary part of the numerator gives me mu squared. Well, I'll write equals here since I won't drop factors from now on. K squared minus mu squared squared plus mu squared gamma squared for k squared near mu squared. Thus we get a characteristic, the characteristic result we also got for scattering amplitudes and non-relativistic theories near an unstable energy level. We get the characteristic Lorentzian line shape or Breit-Wigner shape in k squared, very sharply peaked near the mass of the unstable particle, with a width depending on the parameter gamma. You may be a bit disturbed because you remember that the full width at half maximum is supposed to be, in the ordinary non-relativistic analysis, is supposed to be gamma, and here it looks like it's 2 mu gamma or something like that. But that's simply because we're writing things in terms of the invariant mass squared, k squared, of the state that's produced. If we wrote things in terms of the center of mass energy of that state, that is to say, if we chose the 4-vector k to be E0, then k squared minus mu squared, let me see the computation, in fact, just to make sure I'm doing it right. Yep. Equals E squared minus mu squared, to no one's surprise. I don't know why I had to look that up. Equals E plus mu times E minus mu. And since E is supposed to be close to mu, I can approximate this as 2 mu E minus mu. Thus, writing it on this side here for the moment, because k is near mu. And thus, writing it on this side, k squared minus mu squared plus mu squared gamma squared is approximately equal to 2 mu times E minus mu plus, 2 mu quantity squared times E minus mu squared plus, I've divided gamma squared over 4. which is, of course, now the conventional Breit-Wigner denominator, aside from this factor in front, the conventional Breit-Wigner denominator with the 1/4 where it is in the conventional formula. In terms of energy, we have exactly the same kind of peak. It's supposed to be the same curve. If it looks different, that's just because I'm a bad draftsman. And gamma is indeed the full width at half maximum, just as it should be in the conventional Breit-Wigner formula. Is everybody happy with this? It's just the apparent unconventionality of this thing is just because this is the width in k squared rather than the width in e. Questions? Yes, sir.
Yeah, I had a question here when you have the pole moving off the axis. If you compute gamma to all orders in E, then does the pole really occur at that position given by that?
No, it'll of course have higher order corrections. It'll wander around.
Right, but if we put, are there corrections other than the ones that are in gamma to all orders?
Well, you have to be careful when you compute gammas to all orders, because as soon as you get involved diagrams that involve internal meson lines, you get funny things going on because those meson lines can be on the mass shell in the range of integration. So if you really go on computing gamma, pretty soon you will start computing amplitudes that have funny singularities in them. The computation cannot be carried out to all orders. The best way, if you want to compute gamma to all orders for some exceptionally refined computation, is to just compute the propagator to all orders, which leads you to no ambiguities, along the real axis, extrapolate it into the complex plane and see where the pole is. Okay? Other questions? Are people looking baffled again? I thought this would be a simple lecture after the... maybe it's just I've lost my touch. It happens sometimes. It happens to Joe Namath. I have a sprained tongue. Now, this takes care of the Breit-Wigner formula, which is one of the two hallmarks in non-relativistic scattering theory of the occurrence of an unstable state. We have, granted, not done a general scattering experiment, but a very idealized production experiment. We get a phi prime hammer and hit the vacuum with it and see what comes out. But as expected, what comes out, distributed momentum, has the or in center of mass energy, has the characteristic Breit-Wigner shape. Now, the second hallmark of the occurrence of an unstable particle, and indeed the one that was the first one used, say, in the studies of radioactive nuclei when it was discovered in the late 19th century, is the exponential decay law. Let's see if we can think up a simple thought experiment that will enable us to see the exponential decay law if it is there. Well, suppose we actually wanted, as an experimenter, to measure the lifetime of some unstable particle, say a radioactive nucleus, or if you want to be more glamorous, a K-meson or something like that. How would we do it? Well, first we'd make a K-meson in some specific region with some well-defined momentum. This is already rather tricky. Typically, you send a high-energy accelerator beam into a target around this size, or maybe a bit larger, and all sorts of junk comes out. And then you put in all sorts of magnets and various devices designed to do momentum filtering to make sure you've only got K-mesons coming out at the other end. You somehow extract out only things which lie in a certain portion of momentum space, because clearly when I hit the target with the beam, there will be all sorts of things coming out that I'm not interested in, like pi mesons and fragments of the target, several atoms, molecules boiling off the sides. I don't want them, I just want the K-mesons. Then I go down the beam a certain distance, and I see I have a K-meson detector, and I see how the population of K-mesons falls off as I move the detector further and further down the beam. And if I'm lucky, I will plot a curve that will have a nice exponential in it, and then by looking at the parameters of that exponential, I will see the decay law. Now, that's a rather complicated experiment. Let's idealize it a bit. Firstly, we want something that makes things localized in a certain region of space and time, and also localized in a certain region of momentum space. We'll use exactly this kind of production process to do that. That's not a very realistic production process. People do not have things coupled to scalar fields in general, but it's one which we can manipulate very simply analytically. So the first thing I'll do is I'll make my state by taking the vacuum and hitting it with some source that makes a bunch of states. F of x is some function that I want to have two properties. I want it to be reasonably well localized in x space. I'll draw that symbolically like this. This is in space and time. It's supposed to be some reasonably well localized function, so I know that I've made the particle at the target and not someplace else. And I also want it to be reasonably well localized in k space. So you can imagine it as a Gaussian in all four variables, although that won't be relevant, times some mean value of k I'll call k bar. And I want to make sure I'm looking at k mesons and not 2 pion states or a fragment of the target or something like that coming out. So I'll arrange matters so that k bar squared is near mu squared. In particular, I'll assume that this is sufficiently sharp in momentum space that throughout the relevant region of momentum for this production process, I can use this approximation for the propagator, my single assumption. Okay, I can certainly always do that. That may mean I have to have a fat target in position space, but we'll see that's no problem. Now, that's the production apparatus. I have produced this state. Well, actually, I've produced this state with some tiny coefficient and mainly vacuum, but vacuum I won't detect. Now I want to do the detection apparatus. Oh, so significant points, I should say. F is real. Which, of course, implies that F twiddle of k equals F twiddle of minus k conjugated. Now, what about the detection apparatus? Well, for the detection apparatus, I'm very economical as a theorist. Instead of inventing a new detection apparatus, I'll use the same thing. After all, this formula tells me that if it has a given amplitude for making k mesons, it has an amplitude of the same magnitude for absorbing k mesons of the same momentum. K mesons are zilch, anything of momentum k. So I'll just move myself down the beam by a distance y, space-time distance y, and set up a detection apparatus. And the amplitude I wish to study, which is a of y, is therefore vacuum integral d4x prime d4x. Here's the state I want to find out whether it has, what amplitude it has for going into. F of x prime minus y, phi prime of x prime, f of x, phi of x, vacuum. That is to say, I make some state with this apparatus. I have this identical piece of apparatus that I have down the beam. Perhaps a space-time diagram would be useful. That's just convenience. I could have used another kind of detection apparatus, something that does absorb k mesons, though, or whatever the unstable particle is. So here's the space-time region in which f of x is concentrated. And way down here, some huge distance, so these have no chance of overlapping. Here's the light cone. Of course, I want it to be time-like. Is the point y, and here is the point 0. And this is the region where f of x is significantly different from 0. This is the region from which f of y is sufficiently different from 0. Okay, that's the apparatus. I have something, I have something else. I look at the inner product to find out what the amplitude is. Okay, is everybody happy with this idealized experiment? I only have one function in the problem, one free variable in the problem, y. How far down the beam in space and time I can move my detector. And I want to see what the dependence of this thing is on y. Now, of course, this is something that I can compute in a moment in terms of the Fourier transform of f and the two-point function, phi prime of x, phi prime of x prime, which I also presumably know. So, and I'll just write down the answer. It's a trivial Fourier transform operation. A of y equals minus I integral d4k 2 pi fourth, to nobody's surprise, f twiddle of k squared, that just comes from the Fourier transform of this and the Fourier transform of this, e to the minus I k dot y, that comes from shifting this in Fourier space from x to x minus y, and of course the propagator, which I have assumption is 1 over k squared minus mu squared plus I mu gamma. That's the answer. I can insert this approximation for the propagator legitimately because I assume f of k is concentrated near k bar. Now, yes? Questions? Any questions? I mean, I don't expect you to see the 2 pi's, but they're going to be totally irrelevant. I'm going to just replace them with proportionality signs in a very short moment. This just comes from putting in the expression for this thing as the Fourier transform of the propagator and doing the x and x prime integrals. Now, if we didn't know anything about quantum field theory, but just knew we did this kind of experiment, we had a production apparatus that produced particles in a restricted range of momentum and a detection apparatus that only detected particles in a restricted range of momentum, and we were asked to guess the asymptotic properties of this expression for large y. Y goes down the beam. Say y squared goes to infinity. And we were what would we guess them to be if we were extremely naive? Well, let me define a quantity S. Whoops, I'm sorry. I said something that was a lie. I forgot a critical step. Stop, run back, time slip. T, because y is downbeam from x, I can put a T in here, and then I get this formula. Someone should have asked me about that. Okay, sorry. Here you see y is definitely in the future light cone. What would I expect my amplitude to look like as a function of S naught? Well, as an experimenter, I would say I put a big fat proportionality sign because I got this creation and detection apparatus from a theorist's workshop, so I don't know its properties or its resolution or anything like that. But then I would expect, well, the particle is traveling at proper time S naught, and it has mass mu, so I'd expect there to be a phase factor from the good old Schrödinger equation. Then it's an unstable particle, and it decays. So I expect this. If it's an exponential decay law in the square of the amplitude, it's got to have half that magnitude in the half that exponential in the amplitude itself. And if I'm a very sophisticated experimentalist, I know that from my studies of the Schrödinger equation that wave packets tend to spread out for a large time, such that the amplitude goes down like 1 over time to the 3/2. So I would insert in here to account for that spreading out of the wave packet. So when this is really very far down beam, portions of the decay products miss the miss the detector, 1 over S naught to the 3/2. Okay, this is dumb guess based on the picture that I am making an unstable particle which is traveling around like an ordinary particle, developing a phase, spreading out, but it's got this little extra feature, it decays. Okay, so the longer I wait, the longer it takes it to decay. I seem to have eaten the there we are. Here we are. Now, are there any questions about this guess? Yes?
Yeah, speaking of depth experimentalist, I missed the explanation for the first exponential.
Oh, well, I say in the center of mass frame, it's a particle of mass mu. It gets a phase according to its energy. The longer down beam I wait, the larger the phase is developed. That's E to the minus IET. Yes, sir?
Why would we have power?
Oh, well, that's a fact about the Schrodinger equation, that for a large time, Schrodinger wave packets spread out like 1 over S naught to the 3/2. Essentially, it just comes from the conservation of probability. They have to be spread because if they're localized in position, they're not localized in momentum. Therefore, the position space shape of the wave packet spreads out, and the rate at which the center is moving along at some fixed rate, the rate at which the boundaries spread out depends on the momentum spread. But they spread out at a fixed rate in time. Okay, therefore, if we wait for a very long time so that the spread is important and the original size of the wave packet is not, the extent of the wave packet is linearly proportional to the time. The volume is therefore 1 over time cubed, and the average probability density is 1 over time to the 3/2. Okay? Is everybody happy? This is for a large Y. Now I will show you that this is precisely the form of the asymptotic form for a large Y squared of this expression. That requires some analysis, and I will use one analytical tool and one trick. The analytical tool is the so-called stationary phase approximation. Yes, those hisses are from people who saw it used 12 times in 251. I will explain this for those who did not have the privilege of being confused by me in 251. If we have an integral e to the I f of t, g of t, dt, and f of t is rapidly varying, that is to say, rapidly varying compared to the rate at which g varies. Then in general, this integral will be zip, nothing. Because as I go along in t, f of t is varying rapidly, the phase factor is oscillating up and down, and it averages out to 0. The one exception is points of stationary phase, where the derivative of f is 0. And at such points, of course, this thing is not rapidly varying. It ain't varying at all. Therefore, the integral is dominated by stationary phase points. I will assume there is only one such point, which I'll call t0, df dt at t0 equals 0. If there are several, you get a sum from the several of them. People normally like to phrase this by putting a parameter lambda in front of f of t and say we're studying large lambda. That's neither here nor there. There may not be an adjustable parameter in the theory. It's just that if f of t is varying very rapidly and g of t is not, this is a good approximation. We therefore approximate the integral by its value near the stationary phase point. If I call the integral I, the stationary phase approximation, I equals e to the I f of t0, g of t0, times the integral dt, e to the I f double prime of t0 over 2 t minus t0 squared, The integral is trivial. It is a complex version of a Gaussian. And it gives us e to the I f of t0, g of t0, square root of 2 pi over f double prime of t0. I don't expect you to follow the algebra, but you can check it at home. I hope you do. E to the I pi over 4. Yeah, if f double prime is 0, we have to think again. We have to expand out to the quartic term, or cubic, whichever is the first non-vanishing one. Yes, sir?
Yeah, don't you have to worry about the returning square roots and perhaps taking the minus on that?
Well, I may have made an error, but it's always either one or the other. The point is, if you know the sign of this thing, if it's positive or negative, you know how to rotate the contour in the complex plane to become a Gaussian. And if it has one sign and the other sign, one sign you rotate it this way, the other sign you rotate it this way, those turn out to cancel out and just give you this times a universal factor, as I recall. It doesn't matter anyway. We're going to absorb all these phases into the proportionality sign when we do our equation. It obviously, no, come on, the integral, no, I can't say that. I was about to say it's obviously even, but it isn't. Forget it. I think it's always the same sign. Now, this is our first trick. Our integral is of stationary phase form because we have k dot y here, and y is getting huge, all 4 components. So we have 4 integrals we can do by stationary phase, but before we can do that, we're going to have to put a trick. We have a problem because we're also near k squared equals mu squared, remember? So we can use this approximation. And therefore, the phase of this thing is also changing rapidly over the region of integration as we pass by the pole. Changes by 180 degrees very rapidly if gamma is very small. We certainly don't want to find an approximation that's good if y squared s naught is very large compared to gamma inverse, because then we'll properly get 0. So we somehow want to put the phase variation of the propagator into a form where we can treat it by stationary phase, and that is easy. That's the trick. Now I've got to define my things just right. Well, I'm going to start systematically dropping constant factors, so I guess I'll just use a proportionality symbol. I introduce a parameter s, ds, e to the I, s over 2 mu, y scale it by 2 mu, it will come clear later, k squared minus mu squared plus I gamma mu. Okay, that puts the phase variation, that turns my 4-dimensional integral into a 5-dimensional integral, but but what I gain from that is putting the phase up in the integrand where I can treat it by the stationary phase formula. Now let's go. Absorbing all constants into proportionality signs,
Is there any reason you just write e to the I log of that? Is there any reason why you don't just write e to the I log of the, you know?
I didn't think of trying that. I mean, this is an argument I cooked up last night. It might also work out. I don't know. Well, you can try it. I mean, that log is a funny thing because the thing is changing sign. The logarithm also has a rapidly varying phase. That won't work because the thing is getting close to 0 as k squared gets to mu squared. Okay. But no, it might work. I don't know. Try it. This works well. This is my trick. You have your own trick. Okay, so now we've got our amplitude. I'm going to drop all constant factors, all merely multiplicative factors that depend on mu and gamma. So I have integral d4k f of k squared e to the minus I k dot y integral from 0 to infinity ds, e to the plus I s over 2 mu k squared minus mu squared plus I gamma mu. Now, the first step is to do the k integral by stationary phase. Can now do that. It's rather trivial, since there are just two phase factors that involve k, this one and this one. I will do all 4 k integrations at once by stationary phase. Well, differentiating this thing and this thing to get the phase is pretty trivial. S over mu k naught, the value of k at which the phase is stationary. That comes from differentiating this, minus y equals 0. That is the point at which the phase in the k integral is stationary. Notice that this formula looks very much like the formula for a classical particle of momentum k naught, reaching a point y. You obtain the 4 velocity by dividing the momentum by mu, multiplied by the proper time, and you find the transit point. What? That's right. We'll see what happens in a moment. You're right. At this point, this is just a suggestion caused by my notation, but we'll see what happens to that suggestion. This defines k naught. Y. Now we put in the stationary phase thing, keeping our proportionality signs. We have just the S integral left. F twiddle of k naught squared. We have to put in y, the formula for k naught, which is mu over sy. So this term gives me mu y squared over s. And so does this term, except with a 1/2. So I have e to the minus I over 2 mu y squared over s. That's the value sticking in k naught for k. And then I have e to the I s over 2 mu I gamma mu plus minus mu squared. That's the remaining part that wasn't affected in my stationary phase integral. Then I have all these 2 pi's, which thank God I can forget about. And I have 1 over the square root of the second derivative. The second derivative is s. We're doing 4 integrals at once, dk naught to dk 3. So I get 4 factors of 1 over the square root of s, or 1 over s squared. That does the first stationary phase integral.
Why is it e to the minus I over 2?
Well, this gives me that thing with a plus 1/2, and this gives it with a minus 1. Plus 1/2 plus minus 1 is minus 1/2. Now we're ready to do the S integral, also by stationary phase, because as we see, the S integral is rapidly varying because it has this gigantic factor y squared in it. So we find the stationary point of the S integral. Now, what's the stationary phase point, which I will, of course, consistent with my notation, call S naught? Well, I have to differentiate everything that depends on S and has a phase, not this. This is a real number, but this part here, I should say this is 1 over s squared, not in the exponential, with respect to S. So I have minus 1/2, and another minus sign because that's a 1 over f, mu squared, no, mu y squared over s squared plus mu squared times this, that's an overall minus sign, s over 2. So I have minus 1/2 mu period equals 0. And this determines S naught, the point of stationary phase of the S integral. Yes, sir?
Asking about the previous stationary phase argument. I don't see how when you differentiate those exponentials you get that. Why is that K0?
K0 is the point where this is stationary, where the phase is stationary. So I differentiate with respect to all 4 components of K. I'm doing 4 of them at once to confuse you. K dot y minus S over 2 mu K squared equals 0 at K equals K0. Okay, is it now clear to you? Good. In case someone else catches on, I'll erase it. Now, this integral is very easy to determine what S0 is. S0 squared equals y squared, or S0, since the range of the integral is positive, is the positive square root of y squared. I now plug that into my integral and we're left with no integration at all. Firstly, I evaluate everything at S0. A is proportional to F twiddle of K naught, which is mu, now S has been set equal to S0, mu over S naught y, quantity squared. I see I started too early, so I'll put a times here. Now these two things at S equals S0 are equal. Y squared is S. So there are two things that coincide, this term and this term. And I simply get e to the minus I mu S0. That takes care of this and this. That's evaluated at S equals S0. This term I see I times I is minus 1. The 2 survives. The mu cancels. E to the minus gamma S0 over 2. Now I have a 1 over S0 squared left over. And I still have the square root of the second derivative. The second derivative, this is the first derivative up here. I differentiate once more. I get y squared over s cubed, which is S0 squared is y, so the second derivative is 1 over S0. The square root of the second derivative is therefore 1 over the square root of the second derivative of S0 to the 1/2 times numerical factors, which I absorb in the proportionality sign. And I have completed the integral. Any questions about any stage of this operation? Now, you may notice that our dumb guess was not so dumb after all. We have obtained. Here's the factors that depend on the details of the experimental apparatus that is producing and detecting our unstable particles. Here is the evolution of phase. A particle of mass mu marches along in time. Here is the exponential decay factor, and here is 1 over S0 to the 3/2, the spreading of the wave packet. You may not have followed every algebraic step, but I hope you followed the general method so you can reconstruct the algebra at home if you are so inclined. And I hope you have understood the physical import of what we have obtained. We have derived the exponential decay law. The statement that the propagator in a certain region of K-space can be approximated by the expression we put on the board is 100% equivalent to the statement that under the physical circumstances in which we observe an exponential decay, we would expect to observe an exponential decay law, we do observe an exponential decay law. Yes, sir?
The experimentalists would guess that mu being the mass of the particle, and the mu that we derived over here is just something we put in at the report and happens to coincide with the experimental.
Well, it's the place where the real part of the self-energy vanishes.
Say that again?
It's the place where the real part of pi prime vanishes, the real part of d inverse vanishes. Okay. That's what comes out. That's the mu. That's the place where the real mu, k squared equals mu squared is that point at which the real part of d inverse vanishes. Equivalently, to the order of our approximation, where we assume we can approximate d inverse by this thing in some range of k, it is the real part of the location of the pole. And gamma over 2 is the imaginary part of the location of the pole in k squared. Okay, that is the mu. Okay? It's the mu that appears in the approximate expression for the propagator. Yes, sir.
My question is, if we continue with the method of stationary phase, we can generate a series of correction terms for that trip.
That's right.
And also,
They will all fall off more rapidly than exponential.
yeah, the exponential decay law in quantum mechanics comes from just the first order perturbation theory. I believe we obtain correction using high order.
No, first order time-dependent perturbation theory, you get a linear decay law.
I'm thinking, I guess, of radius of decay, where you get an exponential decay to first order if you just consider, for example, a balanced state of an atom decays by emitting a photon. But if you look more carefully, you get a correction to that.
No,
The question is, you get the
no, this is a famous false statement in the literature. It is true that there are satellite terms in this expression that are non-exponential. These satellite terms have the proper physical well, first, of course, there could be several unstable particles in the same energy range, so like the K1 and the K2, or the K long and the K short, in which case you do indeed get a superposition of two exponentials. There are satellite terms that fall off. This is because even if you've done the most refined momentum analysis, you do not know in the K meson experiment that you are really making a single K meson. You might also be making 2 pi mesons that just by chance have the same energy as the K meson. After all, 2 pi mesons is 2 free pi mesons. Okay? Therefore, as you move your experimental analysis apparatus downstream, you will, of course, get terms that correspond to 2 pi mesons falling off, 2 pi mesons being produced here, spreading out. Okay? And there's a chance that both of them will be in the right position to be picked up again here. That is the interpretation of those satellite terms. They are experimental background. Experimentalists know about them, and they take account of them. Okay? They say, are we really sure we're getting a K meson and not, our apparatus is not... They design their apparatus so that they carefully winnow out those 2 pi meson terms. But they would be there in our Gedanken experiment. They would come out in higher orders, and we have to, those are the corrections. The exponential decay law is 100% valid.
Well, perhaps I'll speak about that later. That's non-relativistic quantum.
What?
I'm thinking...
In non-relativistic quantum mechanics, the same story applies. What do you think all those numbers that appear in tables for radioactive nuclei? A lot of them decay by gamma emission.
Oh, yeah, sure. Because I thought it was just a very close approximation. Because I've seen it derived in a place where an approximation was needed again.
Yeah, well, an approximation is needed to get it here, which we carefully set up. All of our experiment, well, firstly, there's large y squared. That's no approximation. That's something we control. Okay? Yeah. Those other terms would go to 0 as y squared more rapidly as y squared goes to infinity. What some people do is that they set up a thought experiment where they aren't as careful as I have been to put a good momentum filter in at the beginning and at the end. Okay? If you do that kind of thought experiment, then you would get, in fact, a very large contribution from making 2 pi mesons with a mass, say, half that of the K, because then you haven't got a sharp momentum spread. So, of course, what you mainly do is not make K mesons, but make pairs of pi mesons with all sorts of energies. And of course, your experimental apparatus has been built up so that it has a nice probability for detecting pairs of pi mesons as well as detecting K mesons, because it isn't sharp in momentum either. And then you get a mess. And you say, if you're dumb, you say the exponential decay law is just an approximation. Okay? You've got to do this kind of experiment where you hook things up so that you only get momentum near the peak of the Breit-Wigner peak. Then you suppress those things enormously because those uncorrelated pi mesons are just, randomly distributed in phase space, more or less. Okay, if you don't do that, then you'll get something that looks very different. And there are papers in the literature by quite bright people 20 years ago when this thing was not so well understood that said, hey, the exponential decay law should not be true. There should be terms, for example, that go off as inverse powers of the time that should dominate for a large time. Someone as bright as Abdus Salam once suggested this. And that's because he just Fourier transformed the propagator without putting in these f of k's. When you Fourier transform the propagator, if you don't put in this momentum spread, if you just have a sharp position experiment, then you get an enormous contribution from the 2 pi meson states, because then you can make, in particular, 2 pi mesons a threshold. 2 pi mesons a threshold have small relative velocity, and therefore do not spread very much from each other. And if you work things out, you get a 1 over s to the 6th term coming in with a tiny coefficient. And he said, look, it's not the exponential that's the leading term. If you go out many, many lifetimes, you get a 1 over s to the 6th term. And that's just wrong. That's the threshold singularity he was seeing, not the pole on the second sheet. Are you with me?
Yeah.
Okay, good. Okay, so there's an error in the literature. I'm sure this is no surprise to you, but on this particular point, there is this particular error on the literature. Yes, sir?
You're imposing on F that it both be narrow in position and in momentum space.
Well, I don't really demand that it be particularly narrow in position, because if it's flabby in position and spread out, I can always compensate that for that just by letting y get larger and larger. Okay, in actual circumstances, this is a trivial restriction. I mean, the width of the... We want it to be sufficiently narrow in momentum so that the approximation for the propagator is valid. That means it's roughly on the order of the Breit-Wigner peak, or perhaps even smaller if we want to be nicer. Okay, and that means for even something like a K-meson is what, a few electron volts. Whereupon typical macroscopic detection in an apparatus is several centimeters at a minimum and dimension. So there's no problem with the uncertainty principle there. Okay. So there is... and of course, even if there were some problem with the uncertainty principle, it doesn't matter. I could always get around with it by making y big enough. All I demand is that y is so big that there's no significant probability for my detector to overlap my production apparatus. Obviously, I've got a badly designed experiment if that happens. If the width gets very big, of course, then what happens is not on this level, but simply if gamma is so enormously huge, if gamma is 200 MeV or 1,000 MeV or BeV or something like that, then I've got no right making the approximation in the first place in any region of the real axis. Okay. And then the terms I've ignored will probably change significantly over the width of the Breit-Wigner peak. And I can't write d prime as simply a pole term. And indeed, if the width gets very large, the whole idea of an unstable particle begins to disappear, and it just merges in with the background. So you don't have a nice, sharp Breit-Wigner peak standing up out of a smooth, phase-space dominated curve. But as the width gets larger and larger, it merges with the background and eventually gets lost in the crowd. Yes, sir?
If this to be real, and also have a peak at K bar, wouldn't have a peak at minus K bar?
Yeah, that's right. That's what enables me to use the same apparatus for production and detection. It's as good an absorber as it is an emitter. Yes, double peaked. That's right. But as far as the production process goes, only those things that are on the forward light cone come in. As far as the detection process goes, only the momentum Fourier transform, components of the Fourier transform on the backwards light cone come in. I've just arranged matters for convenience. Yeah, I could have a separate f and a g, and then instead of this thing, I would have f of k, g, twiddle of minus k, start. Now, this concludes everything we are going to say in the world in which there are only scalar particles. Next week, we begin studying particles with spin.
Can I ask you a question about the...
That was